Chapter 2: Chronicles of Cosmic Evolution. We continue our meditative journey through the silence of the universe, where each new spiral of knowledge reveals to us not only the abysses of space but also the abysses of our own understanding. If the first chapter was an immersion into the question, "Why are we alone?" then the second shall become a slow, deliberate exploration of how the universe is structured, the universe in which this question could even arise. Our path begins not with loud discoveries, but with a quiet realization. To hear the universe, one must first learn to see it differently. And here we are aided not only by giant telescopes but also by tiny satellites, CubeSats, these humble messengers of human curiosity, no larger than a showbox. To overcome the great filter, we need to integrate knowledge. Subscribe now and become part of the collective wisdom that will ensure our survival in space. Thank you. They remind us that greatness lies not in size, but in intent. Once confined to low Earth orbit, today they penetrate deep space, accompanying larger missions like Quiet Shadows, gathering data where humans have not yet set foot. Their emergence is not merely a technological breakthrough, but a shift in consciousness. We are learning to explore space not only with grand leaps but also with small, constant steps, like water wearing away stone. The first such step beyond Earth's orbit was taken by two CubeSats, Marco A and Marco B, which accompanied the landing of the InSight module on Mars in 2018. They flew alongside, like faithful sentinels, transmitting data to Earth about entry, descent, and landing. Their success was not just an engineering victory, it was a sign. Even small forms of intelligence can participate in the great cosmic dialogue. And now, as the Artemis program prepares to return humans to the moon, CubeSats await their moment. They will measure space weather, search for water ice in the eternal shadow of craters, preparing the way for those who will come after. There is something meditative in their humble work. They do not rush, they do not make noise, they simply gather data, drop by drop, like a monk recording the wisdom of the ages. But CubeSats are only the beginning. Our gaze stretches further, beyond the moon, beyond the asteroid belt, even beyond Pluto, to that region where the sun's dominion ends and the realm of cold and silence begins, the Oort cloud. Imagine a sphere of trillions of icy bodies, surrounding our system at a distance thousands of times greater than that from the Sun to Pluto. This is the boundary of our home, the final frontier beyond which stretches the interstellar void. No probe has yet reached it. Even the voyages, symbols of a search stretching into infinity, are only at the beginning of this journey. The journey to the Oort cloud is a voyage lasting centuries. Modern engines are too slow, communication too weak, the mission timeline longer than a human life. But the very idea of such a flight makes us ponder, what is time to the universe? And what is time for a civilization that hopes to survive? We begin to dream of probes capable of flying for centuries, of missions planned for generations, of ships that could be renewed en route, like a living organism. This is no longer mere exploration. It is a test of our ability to think on universal scales, to plan beyond the span of our own lives. And here we encounter another phenomenon, the private exploration of space. For a long time, space was the domain of states, but now companies are entering it, driven not only by scientific interest but also by entrepreneurial spirit. SpaceX, Blue Origin, other private players, they are changing the rules, accelerating the pace, lowering the cost. But in this race, there is also danger. Space could become not a place for contemplation, but an arena for competition. Our meditation reminds us, it is important not just to fly faster and farther, but to fly mindfully, remembering the fragility of the worlds we explore and our responsibility for the future we are creating. Private companies bring new ideas, new resources, new energy into space, But with them come new questions. Who will regulate activity in deep space? Who will protect potentially habitable worlds from contamination? Who will decide what is valuable, scientific knowledge or commercial gain? We do not yet have the answers. But the very fact that we are asking these questions is already a sign of maturity. We are beginning to see space not as a boundless field for expansion, but as a complex, fragile system requiring a wise approach. And here we return again to CubeSats, quiet, small, inexpensive. They could become not only tools of science but also guardians of ethics, monitoring human activity in space, reminding us that every action we take there has consequences. Meditating on these themes, we feel our consciousness expanding, from a tiny satellite to the boundaries of the solar system, from an engineering task to a philosophical question. And this is only the beginning of the chapter. We allow our consciousness to drift further back, beyond the boundaries of our system, beyond the birth of the sun, to the very beginning of everything. We prepare for a slow, profound immersion into the story of creation, a story not of days, but of epochs, written in the language of physics on the canvas of space-time. Imagine, for a moment, not emptiness, but complete nothingness. No space, no time, no matter. Not even darkness, for darkness implies the absence of light, and here there was nothing to be absent. Then, in an unimaginably distant past, about 13.8 billion years ago, an event occurred that we call the Big Bang. But let go of the familiar notion of an explosion, a bomb scattering fragments into pre-existing space. No, the Big Bang was the birth of space and time itself, emerging from a point of unimaginable, infinite density and temperature, a singularity. From this moment, everything we know, our entire universe, began to expand rapidly, and it continues to do so to this day. In the very first fractions of a second, intervals so minuscule they defy comprehension, trillionths of a second, the universe was a seething cauldron of pure energy and fundamental particles, too hot and dense for even atoms or their nuclei to exist. It was an era ruled by exotic particles like quarks and gluons, floating in a primordial soup. The laws of physics as we know them were perhaps only just forming. The universe expanded at an incredible rate, cooling as it did so. Within mere microseconds, it became cool enough for quarks to combine, forming protons and neutrons, the building blocks of future atomic nuclei. But the universe was still too hot, a dense, opaque plasma of ionized gas where electrons were torn from nuclei and roamed freely, constantly interacting with light, with photons. Imagine an impenetrable fog through which nothing can be seen. This is what the early universe was like for light. Minutes passed, and the universe continued to cool. Approximately 3 minutes after the beginning, the temperature dropped sufficiently for protons and neutrons to begin fusing, forming the first light atomic nuclei, mostly hydrogen, a single proton, and helium, with trace amounts of lithium. But electrons were still free, and the universe remained an opaque plasma. This process of primordial nucleosynthesis determined the initial chemical composition of the universe, which we still observe today. Then came a long period, about 380,000 years, during which the universe continued to expand and cool. And finally, a key event occurred, the epoch of recombination. The temperature had fallen so low that free electrons no longer had enough energy to resist the attraction of atomic nuclei. Electrons settled onto nuclei, forming the first stable, neutral atoms, predominantly hydrogen and helium. This was a turning point. As electrons bound into atoms, they ceased constantly scattering photons. The universe, once a murky plasma, suddenly became transparent to light. The light that had been trapped in the fog could finally travel freely through space. It is this most ancient light that we observe today as the cosmic microwave background, a faint glow coming from all directions in the sky, a kind of echo of the Big Bang, a photograph of the infant universe when it was only 380,000 years old. But after the universe became transparent, an era known as the Dark Ages began. The light of the ancient background radiation continued its journey, but there were no new sources of light yet. The universe was filled with vast clouds of neutral hydrogen and helium. It was dark, cold, and silent. A lull, it seemed. But it was the lull before the storm, for one force was at work inexorably: gravity. In the initially almost uniform distribution of matter, there were tiny, random fluctuations in density. In some places, there was slightly more matter than average. Gravity began its slow, relentless work, pulling matter towards these denser regions. For millions of years, dark clouds of gas slowly contracted under their own gravitation. Within these condensing clouds, density and temperature rose. And then, hundreds of millions of years after the Big Bang, in the densest cores of these gravitational collapses, temperature and pressure reached such values that thermonuclear reactions ignited. Hydrogen nuclei began to fuse into helium, releasing a colossal amount of energy. The first stars were born. They were likely giants, immensely hot, bright stars composed only of hydrogen and helium. They lived briefly, but their appearance marked the end of the Dark Ages. Their powerful radiation began to ionize the surrounding neutral gas, tearing electrons from atoms. Light returned to the universe, but now it was the light of stars. These first stars were not alone. Gravity continued to gather them together, drawing in new streams of gas, forming the first proto-galaxies, the seeds of the giant stellar systems we see today. Thus, from an unimaginably hot and dense point, through epochs of boiling plasma, primordial soup, and long dark ages, under the action of fundamental laws of nature and the inexorable force of gravity, our universe was born, and the first lights ignited in its boundless darkness, ushering in the era of stars and galaxies in which we live. This was only the beginning of the great cosmic drama. We meditate on this sequence not as a dry list of events, but as a majestic, slow unfurling of potential, the potential for everything that would follow, including us. In this first light, we see not just ancient photons, but a promise of structure, of complexity, of future worlds where questions like the Fermi paradox could one day be asked. Leaving the cradle of the Big Bang and the first sparks of starlight behind, we now embark on a journey through the truly colossal structures that fill our universe, galaxies. These are the giant stellar metropolises scattered across the vast expanse of the cosmos. What is a galaxy? Imagine a colossal island in the universal ocean, a system consisting of hundreds of billions, sometimes even trillions, of stars like our Sun or entirely different ones. But a galaxy is not just stars. It is also an immense amount of interstellar gas, primarily hydrogen and helium, and dust, minuscule solid particles that serve as the building material for new stars and planets. All of this, stars, gas, dust, and also the mysterious dark matter, which we cannot see but feel through its gravitational influence, is held together by the mighty force of gravity, rotating around a common center of mass. Our own cosmic home, the galaxy that contains the solar system and our Earth, is named the Milky Way. If we could look at it from the outside, we would witness a breathtaking spectacle, a vast flat disk approximately 100,000 light-years in diameter, with a bright central bulge called the bulge, and elegantly swirling spiral arms adorned with young blue stars and glowing pink nebulae, regions of active star formation. Our Sun is a modest resident of one such arm, the Orion Arm, located roughly 2/3 of the way from the galactic center to the edge of the disk. We are not at the center of events, but rather on a quiet outskirts of this stellar metropolis, which may, in fact, be for the best for the emergence and development of life. In the central bulge of the Milky Way, true chaos reigns. Stars there are packed much closer together. They are primarily old, yellow, and red luminaries. And at the very heart of our galaxy, hidden from us by dense clouds of gas and dust, lurks a supermassive black hole known as Sagittarius A star. Its mass exceeds that of the Sun by more than 4 million times, and its monstrous gravity governs the motion of stars at the galaxy's core. This entire disk and bulge are surrounded by a vast, nearly spherical halo, a sparse region containing very old stars, globular star clusters, dense groups of hundreds of thousands of ancient stars, and, as is believed, the majority of our galaxy's enigmatic dark matter. The total number of stars in the Milky Way is estimated at hundreds of billions, between 200 and 400 billion. To comprehend such a number is simply impossible. Yet, the Milky Way is but one of countless galaxies in the universe, and they come in a variety of shapes and sizes. Astronomers classify them into several main types. Spiral galaxies, like our own or our nearest large neighbor, the Andromeda Galaxy, which, by the way, resides at a distance of about 2.5 million light-years and is inexorably approaching us for a future merger, are characterized by the presence of a disk, a bulge, and spiral arms. The arms are rich in gas and dust, so new stars are actively born there. Another type is elliptical galaxies. They have a smoother, oval, or almost spherical shape, without a pronounced disk or arms. They consist mostly of old stars, contain little gas and dust, and star formation there has nearly ceased. Elliptical galaxies can be both dwarf and true giants, often located at the centers of large galaxy clusters. They may have formed from the merger of many spiral galaxies. Finally, there are irregular galaxies, which lack clear, symmetrical structure. They often appear chaotic. They may be the result of gravitational interactions or collisions between other galaxies, or simply be small galaxies that lack the mass to form an ordered structure. Galaxies do not exist in isolation. They constantly interact with one another. Gravity draws them together, leading them to form groups and clusters. Our Milky Way is part of the so-called local group, comprising several dozen galaxies, dominated by the Milky Way and Andromeda. Larger clusters, like the Virgo cluster, can contain thousands of galaxies. Sometimes galaxies pass close to one another, distorting each other's forms with gravitational tides, pulling out long tails of stars and gas. At other times, they collide and merge into a single entity. These cosmic cataclysms, lasting hundreds of millions of years, lead to violent bursts of star formation and can completely change a galaxy's type. Galaxy clusters, in turn, unite into even more grandiose structures. Superclusters, which align into giant filaments and walls, surrounding vast regions of relative emptiness called voids. This web-like structure, composed of superclusters and voids, represents the large-scale structure of the universe. As we meditate on these filaments and voids, we feel the architecture of the cosmos itself, a structure born from the subtle fluctuations of the primordial plasma, grown over billions of years by gravity. It is a slow, majestic dance, and our galaxy is but one participant in this ballet of unimaginable scale. Leaving behind the grand clusters of galaxies, let us now bring our gaze closer to the individual luminous points that fill them, the stars. These are the true engines of the universe, the fiery furnaces that serve as factories of light, heat, and the very elements from which all around us is built. The life path of a star is an epic drama unfolding over millions or even trillions of years, beginning in the cold, dark depths of space. Stars are not born in isolation, but within vast, shapeless clouds of interstellar gas and dust, known as giant molecular clouds or nebulae. These stellar nurseries can stretch for tens or hundreds of light years and contain enough mass to birth thousands of stars. Initially, these clouds are cold, mere degrees above absolute zero, and consist mostly of molecular hydrogen and helium, with a small admixture of dust, tiny solid particles. But within these seemingly tranquil clouds lies an inexorable force: gravity. Random densifications, perhaps caused by shockwaves from neighboring supernova explosions or gravitational perturbations, begin to attract surrounding matter. As more gas and dust is drawn to a single spot, this region becomes denser and begins to contract under its own gravity. This process is called gravitational collapse. At the center of the collapsing cloud fragment, a densification forms, a protostar. It is not yet a true star, as thermonuclear reactions do not occur in its core, but it begins to heat up due to the energy of contraction, much like a pump heats up when inflating a tire. The protostar continues to attract matter from the surrounding disk of gas and dust that forms around it due to the conservation of angular momentum, similar to how a spinning figure skater speeds up by pulling in their arms. Temperature and pressure in the protostar's core rise inexorably. And when they reach truly colossal values, millions of degrees and unimaginable pressure, a miracle occurs. Thermonuclear fusion ignites. Atomic nuclei of hydrogen begin to overcome the forces of electrical repulsion and fuse with each other, forming helium nuclei. This process releases an enormous amount of energy in the form of light and heat, which surges outward. This energy creates pressure that counteracts the force of gravity striving to crush the star. A delicate equilibrium is established. A star is born. From this moment, it will shine steadily, burning hydrogen in its core for the majority of its life. It is this process of thermonuclear fusion, the transformation of hydrogen into helium, that is the source of energy causing stars to shine and bestows light and warmth upon the planets orbiting them. Our Sun, for example, transforms about 600 million tons of hydrogen into helium every second. In doing so, approximately 4 million tons of mass are converted into pure energy, in accordance with Einstein's famous equation, a concept whose profound implications we quietly acknowledge here, even as we forego the symbols. Stars, however, are not all the same. Their fate, brightness, color, and lifespan depend directly on one key parameter: their initial mass. There exists a whole stellar zoo. The smaller stars, red dwarfs, have a mass of only 1/10 that of our Sun. They are relatively cool, hence they glow with a red light, are dim, and burn their hydrogen fuel at an incredibly slow pace. Their lifespan can span trillions of years, far longer than the current age of the universe. Stars like our Sun are classified as yellow dwarfs. They are hotter and brighter than red dwarfs, and their life cycle lasts on the order of 10 billion years. At the other end of the spectrum are massive stars, blue giants and supergiants, which can be tens or even hundreds of times more massive than the Sun. They are incredibly hot, shine with a bright blue or white light, are extremely luminous, and burn through their fuel at a furious pace. Their life is a bright but short flash, lasting only a few million years. Yet any star, regardless of its mass, will eventually exhaust its primary fuel, the hydrogen in its core, and then begins the final act of its life, the nature of which is determined by its initial mass. For stars like our Sun, when the hydrogen in the core is depleted, fusion there ceases. Gravity once again gains the upper hand. The core begins to contract and heat up even more intensely. This heating ignites thermonuclear reactions in a shell of hydrogen around the core. The released energy causes the star's outer layers to expand enormously. The star transforms into a red giant. Its radius can increase hundreds of times, potentially engulfing the inner planets. Such a fate awaits our Earth in approximately 5 billion years. Within the swollen envelope of a red giant, new fusion reactions may begin, such as the fusion of helium into carbon and oxygen. Eventually, the outer layers of the red giant become unstable and are gradually shed into the surrounding space, forming a beautiful expanding shell of glowing gas called a planetary nebula, a historical name with no relation to planets. At the center remains only the hot, incredibly dense core of the former star, a white dwarf. It no longer produces energy through fusion and will simply cool slowly over billions of years, eventually becoming a cold, dark black dwarf. The fate of massive stars, however, is far more dramatic. When they exhaust the hydrogen in their cores, they too begin to burn helium, then carbon, oxygen, and so on, synthesizing ever heavier elements up to iron. They swell to even greater sizes, becoming red supergiants. But the fusion of iron is the end point. It does not release energy. Instead, it requires it. When the star's core becomes iron, it can no longer resist gravity. In a fraction of a second, the core collapses with monstrous force. Then, the outer layers of the star plummet onto this compressed core at tremendous speed and rebound from it.
A colossale explosion occure à supernova.
For a brief moment, the star can outshine an entire galaxy. During a supernova explosion, shockwaves and colossal temperatures create conditions for the synthesis of elements heavier than iron: gold, silver, uranium, and many others. The explosion scatters all these elements, created both inside the star during its life and during the explosion itself, throughout the surrounding interstellar space. This ejected material enriches the gas clouds from which future generations of stars and planetary systems will form. This is why we say we are all stardust. The carbon atoms in our bodies, the oxygen we breathe, the iron in our blood, all were once forged in the hearts of long-dead stars and scattered across the cosmos by supernova explosions. But what remains after a supernova? If the original star was sufficiently massive but not overly so, its collapsing core may compress to an incredible density, forming a neutron star. This is an object the size of a small city, but with a mass greater than that of our Sun. Matter within it is so compressed that electrons are pressed into protons, forming neutrons. A teaspoon of neutron star material would weigh billions of tons. Some neutron stars spin rapidly and emit beams of radiation that we detect as regular pulses. These objects are called pulsars. If, however, the original star was extraordinarily massive, then even the pressure of neutrons cannot stop the gravitational collapse of its core. It compresses into a state we call a black hole, a region of spacetime with gravity so strong that nothing, not even light, can escape it once it crosses a boundary called the event horizon. Black holes are invisible in themselves, but they can be detected by their gravitational influence on neighboring stars or by the radiation from matter falling into them. Thus, the great cosmic cycle is completed. Stars are born from interstellar gas and dust, live by burning fuel and creating heavy elements, and then die, returning this enriched substance back into space, where it will become the material for new generations of stars, planets, and, perhaps, life. In this endless cycle of death and rebirth, we find the source of our own existence and the profound connection that binds us to the cosmos. Leaving behind the epic drama of stellar birth and death in the galactic depths, we gently guide our awareness back to our own cosmic home, to the corner of the universe we know most intimately, our solar system. This is our small yet incredibly diverse island within the boundless ocean of the Milky Way. At its heart, reigning supreme, is our Sun, a yellow dwarf star, a true thermonuclear reactor that warms and illuminates all within its reach. The Sun is so vast that its diameter is approximately 109 times that of Earth. and its mass constitutes 99.86% of the entire solar system's mass. It is composed primarily of hydrogen, about 73%, and helium, about 25%, with a small admixture of heavier elements. In its searing core, where temperatures reach 15 million degrees Celsius, the process of thermonuclear fusion ceaselessly continues, transforming hydrogen into helium and releasing colossal energy. This energy reaches us as light and warmth, making life on Earth possible. Without the Sun, our planet would be an icy, lifeless desert, a silent stone adrift in perpetual night. Our very existence is a dialogue with this gentle, life-giving giant, a dialogue conducted across a distance of 150 million kilometers, yet as intimate as the light upon our skin. Closest to this fiery heart orbit the 4 terrestrial planets, forming the inner circle of the solar system. First comes Mercury, a small rocky world, almost devoid of atmosphere. It is the closest to the Sun, and thus its day side endures searing heat capable of melting lead, while its night side is locked in deep, frigid cold. Its surface is pockmarked with craters, testimonies to the violent youth of our system. Next is Venus, often called Earth's evil twin due to its similar size and mass. But there the resemblance ends. Venus is shrouded in a dense, poisonous atmosphere of carbon dioxide, creating a powerful greenhouse effect. Surface temperatures hover constantly around 470 degrees Celsius, hotter than on Mercury. Beneath clouds of sulfuric acid lies a volcanic landscape under crushing pressure, a vision of hellish beauty. The third planet from the Sun is our native Earth, a unique celestial body. It is the only world we know with liquid water on its surface, an atmosphere rich in oxygen, and, most importantly, life in all its diversity. Earth resides within the Sun's so-called habitable zone, a distance that is neither too hot nor too cold for liquid water to exist. It possesses a large natural satellite, the Moon, which stabilizes our axial tilt and gives rise to the tides, a silent celestial partner in our planetary dance. The fourth planet is Mars, the red planet. Its color comes from iron oxide dust covering its surface. Mars is smaller than Earth, with a thin atmosphere of carbon dioxide and a frigid climate. Yet, in the distant past, Mars may have been warmer and wetter, with rivers, lakes, and perhaps even oceans. Today, scientists actively search for traces of this ancient water and possible signs of past, or even present, microbial life beneath its ruddy soil. Mars is attended by 2 tiny, asteroid-like moons, Phobos and Deimos. Between the orbits of Mars and Jupiter lies the asteroid belt, a region populated by millions of rocky and metallic bodies of varying sizes, from dust grains to the dwarf planet Ceres, which has an almost spherical shape. This is not the debris of a shattered planet, as once thought, but rather construction material that the powerful gravity of neighboring Jupiter prevented from coalescing into a full-fledged world. It is a realm of silent, ancient stones, a testament to a planetary formation that never was. Beyond the asteroid belt begins the realm of the giants, the outer solar system. First, we encounter Jupiter, the undisputed king of the planets. This gas giant is over 11 times wider than Earth and more than 300 times more massive. It consists mainly of hydrogen and helium, much like the Sun, but lack the mass to ignite fusion in its core. Its atmosphere is a churning ocean of clouds, forming colorful bands and colossal vortices. The most famous of these is the Great Red Spot, a titanic storm that has raged for centuries, larger than Earth itself. Jupiter commands a vast entourage of moons, over 90 known. The 4 largest, Io, Europa, Ganymede, and Callisto, discovered by Galileo, are fascinating worlds in their own right. Io, the most volcanically active object in the solar system, Europa, with its icy shell hiding a potential global ocean, Ganymede, the largest moon, even bigger than Mercury, and Callisto, an ancient, cratered relic. Next is Saturn, perhaps the most recognizable planet, thanks to its magnificent ring system. These rings are not solid disks but consist of countless particles of ice and dust, from grains of sand to house-sized boulders, all orbiting the planet in a delicate, silent ballet. Saturn itself is also a gas giant, slightly smaller than Jupiter. Among its many moons, Titan stands out, the only moon in the solar system with a substantial atmosphere, denser than Earth's, composed mostly of nitrogen. On its surface, rivers flow and lakes exist, but not of water, of liquid methane and ethane, shaped by temperatures near -180 degrees Celsius. It is a world of organic chemistry unfolding in deep freeze. Further out, in the darkness and cold of the outer reaches, move the two ice giants, Uranus and Neptune. They are smaller than the gas giants but still vastly larger than Earth. They are called ice giants because beneath their hydrogen-helium atmospheres lie mantles composed of ices, frozen water, ammonia, and methane. It is methane in their upper atmospheres that absorbs red light, giving these planets their characteristic bluish-green hues. Uranus is unique for its extreme axial tilt. It essentially rotates on its side, likely due to a colossal impact in its past. Neptune, the farthest of the giant planets, is known for its fierce winds, the fastest in the solar system. Both planets possess faint ring systems and numerous icy moons. Yet, the solar system does not end with Neptune. Beyond its orbit stretches the Kuiper Belt, another region populated by icy bodies, akin to the asteroid belt but far wider and more massive. Here reside dwarf planets like Pluto, once considered the ninth planet, Eris, Makemake, and Haumea, along with myriad smaller objects. The Kuiper Belt is thought to be the source of short-period comets, dirty snowballs of ice and dust that occasionally venture sunward, growing bright tails of vaporizing gas and dust. And still further, on the outermost fringes of the Sun's gravitational influence, at distances up to a light-year away, lies the hypothetical Oort cloud, a vast, spherical shell of trillions of icy bodies. It is believed to be the source of long-period comets. In addition to planets, dwarf planets, moons, and asteroids, the solar system teems with smaller objects, meteoroids. When these rocks or dust particles enter Earth's atmosphere, they burn up, creating the bright streaks we call meteors or shooting stars. If an object is large enough to survive this fiery descent, its remnant falls to Earth as a meteorite, a precious sample of cosmic substance. Thus is our cosmic home, the solar system. One star, 8 planets, hundreds of moons, an asteroid belt, a Kuiper Belt, the distant Oort cloud, and myriad comets and meteoroids. A world full of diversity, mystery, and endless objects for further contemplation. It is a perfectly balanced, intricate mechanism, set in motion billions of years ago and continuing its slow, majestic dance, a dance in which our pale blue dot plays its own delicate, vibrant part. Our journey through the solar system has revealed to us a stunning diversity of worlds, yet this is but a tiny pebble on the boundless beach of the universe. It is time to look beyond our comfortable yard, to peer into the depths of the Milky Way and beyond, towards other stars, and to face the uncharted frontiers and eternal questions that stir the human imagination. For a long time, we could only speculate. Do planets exist around other stars? Today we know with certainty, they do, and there are thousands of them. These worlds beyond our solar system are called exoplanets. Their discovery has become one of the most thrilling realms of modern astronomy. But how are they found? They are incredibly faint and lie at immense distances. One of the most successful methods is the transit method. Imagine a planet, orbiting its star, passing directly between it and us. For a brief moment, it slightly blocks the star's light, causing a tiny but measurable dip in its brightness. By observing a star long enough and detecting regular, periodic dips, astronomers can infer the presence of a planet, its size, and its orbital period. Another powerful technique is the radial velocity method, or the Doppler method. Just as a planet orbits a star, the star itself, under the planet's gravitational pull, makes tiny wobbles, moving ever so slightly toward us and then away. These minute motions can be detected through subtle shifts in the color of the star's light. As the star moves toward us, its light shifts slightly toward the blue end of the spectrum. As it moves away, toward the red, the Doppler effect. By measuring these wobbles, the planet's mass and orbital parameters can be determined. Thanks to these and other methods, we have discovered a stunning variety of exoplanets, utterly unlike anything in our solar system. There are hot Jupiters, gas giants orbiting so close to their stars that their year lasts mere days, with temperatures soaring to extremes. There are super-Earths, planets larger and more massive than Earth, yet still rocky. There are water worlds, entirely covered by global oceans, and ice giants reminiscent of our Uranus and Neptune. But the most stirring goal of the search is to find a second Earth, a planet similar to our own, capable of supporting life. A key concept here is the habitable zone, a theoretical region around a star where, given a suitable atmosphere, surface temperatures could allow liquid water to exist, not so hot that it would evaporate, nor so cold that it would freeze. Scientists actively seek rocky, Earth-sized planets within this zone around their stars. Dozens of potentially habitable worlds have already been identified, but confirming the presence of liquid water, let alone life, remains an immensely challenging task, one that awaits future, more powerful telescopes. Yet, even as we learn more about stars and planets, the universe continues to present us with truly monumental enigmas. Two of them dominate modern cosmology: dark matter and dark energy. When astronomers study the rotation of galaxies, they discover that the visible stars and gas rotate much faster than they should, based on their combined mass. Galaxies should tear themselves apart, yet they do not. To explain this, scientists posited the existence of an invisible substance, dark matter, which neither emits nor absorbs light but exerts gravitational pull. It is believed that dark matter outweighs ordinary, visible matter, the stuff of which we, planets, and stars are made, by roughly a factor of 5. It forms an invisible scaffolding that holds galaxies and galaxy clusters together. But what exactly is dark matter? What particles compose it? This remains one of the greatest mysteries in physics. No less enigmatic is dark energy. Until the late 20th century, it was thought that the expansion of the universe, which began with a Big Bang, should be slowing down under the gravitational pull of all matter. However, observations of distant supernovae showed the opposite. The universe is not just expanding, it is expanding at an accelerating rate. To explain this acceleration, scientists introduced the concept of dark energy, a mysterious force or property of the vacuum itself that acts as a form of anti-gravity, pushing space apart and causing galaxies to recede from each other ever faster. By current estimates, dark energy constitutes about 70% of the total mass energy content of the universe. The nature of dark energy is perhaps the most profound riddle in modern science. And, of course, against the backdrop of these cosmic scales and mysteries, the most compelling question inevitably arises. Are we alone in the universe? Is there life elsewhere? There exists the so-called Drake equation. It is not a strict formula for calculation, but rather a way to structure our thinking about the probability of extraterrestrial civilizations. It considers many factors: the rate of star formation, the fraction of stars with planets, the number of planets in the habitable zone, the probability of life arising, the probability of intelligent life developing, the probability of such life developing communicative technology, and the lifespan of such a civilization. We still lack precise values for most of these multipliers, but the equation itself underscores how many factors must align. Nevertheless, given the unimaginable number of stars and planets in the universe, many scientists believe the emergence of life elsewhere is quite probable. The search for signals from extraterrestrial civilizations is carried out by projects like SETI, Search for Extraterrestrial Intelligence, which listens to the cosmos with radio telescopes in the hope of detecting an artificial signal. Another avenue is the search for biosignatures, chemical signs of life in the atmospheres of exoplanets. For instance, the simultaneous detection of oxygen and methane in a distant planet's atmosphere could serve as an indirect indication of biological activity, as these gases rapidly destroy each other unless continuously replenished by living processes. Thus, the search continues, a dual-path investigation into the cosmos. We listen, straining to catch a whisper of intelligence in the radio static, and we look, dissecting the faint starlight that has passed through alien atmospheres, seeking the subtle, unstable chemistry that betrays the presence of life. Both paths are acts of profound patience, stretched across years, decades, and generations of human effort. Yet, this search places us before two immense, silent frontiers. The first is the frontier of space, quantified in light years, a gulf that renders even the nearest stars profoundly remote. The second, less obvious but equally daunting, is the frontier of time. Our radio telescopes listen for signals that may have been broadcast 1,000 years ago from a civilization that has long since vanished into history or transcended its physical form. The biosignatures we seek in exoplanet atmospheres are snapshots of worlds as they were when their light began its journey to us, a journey that may have lasted longer than the entire span of human civilization. We are archaeologists of the present moment, sifting through layered epochs of cosmic history, never knowing if what we detect is a vibrant present or a distant, fossilized past. This realization, that our search is constrained not only by distance but by the deep, silent river of cosmic time, slowly reshapes our understanding of the great silence. Perhaps the silence is not empty, but layered. It contains the silence of distance, the silence of temporal misalignment, and the silence of civilizations that have learned to communicate in ways invisible to our nascent instruments. And so, we are compelled to ask, if we are to have any hope of bridging these gulfs, of reaching across the light years and the millennia, what must we become? Our answer, slowly taking form, lies not only in how we listen and look, but in what we choose to send, and how we learn to think in timescales that match the cosmos itself. This contemplation of layered silence naturally draws our focus inward, to the very tools and concepts we employ in our search. We begin to see that the challenge of the Fermi paradox is mirrored in the practical challenges of our own exploration. To seek others, we must first learn to operate on cosmic scales, not just of space, but of time. Consider the humble meteorite, a fragment of asteroidal or planetary crust that falls to Earth. It is a messenger not from another civilization, but from the deep past of our own solar system. Within its crystalline structure, it carries a chronological record spanning billions of years. By comparing the crater-scarred surfaces of Mars, the ancient, unaltered face of Mercury's Calorus Basin, and the relatively recent icy plains of Pluto's Sputnik Planitia, we construct a geological timeline of our neighborhood. We see that cosmic history is not uniform. It is a tapestry where some threads, the surfaces of the Moon or Callisto, have remained nearly unchanged for eons, while others, the volcanoes of Io or the geysers of Enceladus, rewrite their world's story daily. Against this backdrop, the timeline of human civilization is a single, faint stroke on an impossibly vast canvas. All our recorded history, from the first cities to the launch of the Parker Solar Probe, fits into a span so brief it is virtually instantaneous on the geological or stellar scale. Our technological window for broadcasting and listening to the cosmos has lasted little more than a century, a flicker in the dark. This disparity in timescales is not a cause for despair, but for a profound shift in perspective. It asks us to envision projects that outlive their creators, to plant trees under whose shade we will never sit. Our most successful deep space probes embody this principle. The Voyager spacecraft, now in interstellar space, carry their golden records, messages to a future and an audience their designers will never know. Their power will fade, their instruments will fall silent, but they will continue their journey for millennia, carrying a whisper of Earth into the void. They are more than machines. They are vessels of legacy, testaments to a species that looks beyond its own horizon. This leads us to the next quiet revolution in our thinking, the engineering of patience. To reach farther, we must build not just for distance, but for duration. Concepts once confined to science fiction are now serious subjects of study. Solar sails, propelled by the gentle but unceasing pressure of starlight, could enable decades-long journeys to the outer solar system and beyond without the constraint of finite fuel. The visionary Breakthrough Starshot initiative contemplates using powerful lasers to propel gram-scale star chips attached to light sails to relativistic speeds, a flyby of Alpha Centauri within a human lifetime. The craft would be a fleeting, silent witness, a barely there probe snapping a handful of images as it screams past an alien world, its data taking years to trickle back home. Even more monumental are the theoretical designs for generation ships or world ships, self-sustaining arcs that would journey for centuries, entire human societies living and dying aboard them before reaching their destination. These are not mere vehicles, they are declarations. They state that a civilization values the journey of discovery more than the comfort of the familiar, that it is willing to mortgage its present for a future it will never see. And here, we encounter a deep, ethical resonance with the themes of our first chapter. Sending such long-lived craft, or even the tiny, fast probes of Starshot, is an act that must be undertaken with serenity and profound responsibility. A probe aimed at another star system, however unintentionally, becomes an interstellar object. Could it, in some distant eon, encounter a life-bearing world? Our duty, then, is to ensure our ambitions do not become another civilization's filter. The same ethical caution that guided Cassini's final plunge into Saturn must be scaled to an interstellar level. Perhaps part of achieving cosmic maturity is learning to explore with such cleanliness and respect that our passage leaves no trace, contaminates no future possibilities. Thus, our search for others and our own outward journey become two strands of the same thread. One strand is receptive. We listen, we analyze light, we seek signals. The other is active. We send out our own humble messengers, crafted to endure the silence. One strand asks, "Are you there?" The other whispers, "We were here, and we wondered." In this duality, the great silence begins to feel less like an empty void and more like a medium, a dark, silent ocean across which we are learning to send the most fragile of boats. We may never know if they reach another shore, or if a vessel from another shore is already drifting unseen toward us. But the act of building, of sending, of listening with patience that spans generations, this act itself becomes a form of communication. It communicates the values of curiosity, longevity, and hope. It is how a young, volatile species begins to train itself to think and act on cosmic timescales. We are learning to speak not just with words or radio waves, but with our persistence. Our signal is not just what we broadcast, but what we build to last. And in this long, slow endeavor, we may be quietly answering the Fermi paradox in the only way we can. by demonstrating, through our sustained and careful effort, that we are striving to become the kind of civilization that might one day be worthy of breaking the silence. Thus, our search for others and our own outward journey become two strands of the same thread. One strand is receptive. We listen, we analyze light, we seek signals. The other is active. We send out our own humble messengers, crafted to endure the silence. One strand asks, "Are you there?" The other whispers, "We were here, and we wondered." In this duality, the great silence begins to feel less like an empty void and more like a medium, a dark, silent ocean across which we are learning to send the most fragile of boats. We may never know if they reach another shore, or if a vessel from another shore is already drifting unseen toward us. But the act of building, of sending, of listening with patience that spans generations, this act itself becomes a form of communication. It communicates the values of curiosity, longevity, and hope. It is how a young, volatile species begins to train itself to think and act on cosmic timescales. We are learning to speak not just with words or radio waves, but with our persistence. Our signal is not just what we broadcast, but what we build to last. And in this long, slow endeavor, we may be quietly answering the Fermi paradox in the only way we can, by demonstrating, through our sustained and careful effort, that we are striving to become the kind of civilization that might one day be worthy of breaking the silence. This journey through cosmic evolution, from the first whisper of the Big Bang to our own whispered questions into the dark, has been a meditation on scale. We have stretched our minds to encompass the birth of space-time, the slow accretion of galaxies, the fleeting fire of stars, and the fragile emergence of life on a pale blue dot. We have measured the abyss not only in light years but in the generations it would take to cross it, and found within that measurement not despair, but a new kind of purpose. The chronicle of the cosmos is written in the language of physics, but it is read in the silent grammar of time, deep, patient, and indifferent to our brief lives. To read it at all, we had to learn its alphabet, the redshift of fleeing galaxies, the periodic dimming of distant stars, the fossilized light of the cosmic dawn. Each new symbol we deciphered expanded the story and simultaneously shrank our own chapter within it. We are a footnote in a library of universal history, yet a footnote possessed of a singular, burning curiosity to read the rest of the book. And this curiosity has led us to a profound pivot. We began as archivists, piecing together the universe's past from the fragments of light that reached us. Then we became listeners, holding giant antennas to the sky, hoping to catch a murmur of another mind in the cosmic static. Now, we are becoming gardeners. We plant seeds of inquiry that we will never see flower. We launch vessels whose missions will outlive our civilizations. We design instruments not for our answers, but for the questions of our children's children. This is the true evolution chronicled here, not just of stars and planets, but of a perspective. We are evolving from a species that looks at the universe to one that begins to think with it, in its own slow, deliberate tempo. The great silence, then, is not a verdict of loneliness. It is the blank page after the epic prologue of cosmic creation. It is the quiet in the concert hall before the next movement begins. We have spent this chapter reading the prologue. We have learned its themes: gravity, fusion, entropy, evolution. We have felt its scale. And in the resonant quiet that follows, we face a choice. We can close the book, overwhelmed by its immensity, or we can take up the pen. Our pen, for now, is not a declaration. It is a lens. It is a sensor. It is a precisely tuned instrument of perception. Having contemplated the whole, we now turn, with focused intent, to the specific. Having trained ourselves to think in epochs, we now apply that patience to seeing, truly seeing, the exquisite details of our celestial neighborhood. The philosophy of the long now must manifest in the optics of the immediate. The grand ambition to converse with the cosmos begins with the humble act of observing it, with unprecedented clarity, precision, and wonder. Therefore, we gently close this volume of chronicles. We let the echoes of the Big Bang and the ghostly calls of SETI fade into a respectful background hum. We turn our gaze, no longer the wide, wondering gaze of the child, but the keen, patient gaze of the apprentice, toward the craftsmen of vision, the silent cartographers, and the new eyes we have built to see the universe anew. The meditation on why and whether now gives way to a revelation of how and what. If the first act of our cosmic story was creation, and the second was the long question born from contemplation of that creation, then this third act is perception. It is the act of bringing the universe into a focus so sharp that it reveals secrets hiding in plain sight. It is the chapter of tools and clarity. We begin not with a roar, but with the almost inaudible click of a shutter opening in the deep freeze of space. 1,000,000 miles from Earth, at a gravitational balance point known as Lagrange point 2, a new kind of eye has opened. Its primary mirror, a gilded honeycomb of beryllium, does not simply collect light, it gathers ancient heat. This is the James Webb Space Telescope, and its first deep field was not merely an image. It was a temporal portal. Each faint, red smudge of light was a galaxy seen not as it is, but as it was over 13 billion years ago, in its violent, formative youth. Webb's power is not to make distant things look closer, but to make ancient things appear now. It collapses time, allowing us to witness the universe's childhood, to study the very first stellar nurseries where the original elements of life were forged. It is our first machine capable of seeing the cosmic dawn not as a theoretical event, but as a gallery of individual, struggling suns. Yet, as one eye looks back to the beginning, another is engaged in an act of meticulous, stellar cartography. From a different silent point in space, the Gaia spacecraft does not peer into the deep past. Instead, it measures the present with godlike precision. Its mission is not to find the oldest light, but to map the precise position, distance, and motion of over 1 billion stars in our own Milky Way. Think of it, 1 billion points of light, each with a known address and velocity. Gaia is constructing the first dynamic, three-dimensional atlas of our galactic home. It measures the wobble of stars tugged by invisible planets. It traces the ghostly gravitational signatures of dark matter. It watches as the galaxy itself breathes and rotates, a slow-motion dance it can now quantify. Where Webb is a time-traveling historian, Gaia is a geographer of the present, drawing the map upon which future journeys, real and intellectual, will be plotted. And then, our gaze, now sharpened by these grand instruments, falls upon familiar worlds, only to discover they have been wearing masks. We turn to the ice giants at the edge of our system, to Neptune, long pictured in our minds and textbooks as a perfect, deep azure sphere, the archetypal blue planet. But this, we have recently learned, was a collective illusion, a trick of early imaging, a story we told ourselves. New data, analyzed with modern rigor, has softly pulled away that blue veil. Neptune's true color is a paler, more complex hue, a muted cyan. The planet's iconic appearance was less a fact of nature and more artifact of our own limited perception and our desire for celestial majesty. This correction is a small, humble masterpiece of the new perception. It teaches us that seeing is not passive. It is an interpretive act. And with better tools and more patient analysis, we can correct even our most fundamental visual assumptions. Neptune's new palette is a whisper, look again. What you know is only what you have been able to see until now. This lesson, look again, finds its most profound application closer to home, in the orbit of Jupiter. Here, the moon Europa hangs like a cracked marble. For decades, it has been a subject of tantalizing speculation, a world with an icy crust suspected to hide a global, subsurface saltwater ocean. But speculation is not knowledge. The new eyes have turned to Europa, and they have not merely looked, they have analyzed. Spectrometers have dissected the sunlight reflecting off its frozen surface. And there, in the fractured, young terrain of a region called Terra Regio, they found a simple, momentous signature: carbon dioxide. This molecule, so fundamental to the chemistry of life as we know it, appears to be welling up from within, from the hidden ocean below. It is not a contaminant from an impact. It is a native emissary from Europa's secret sea. This is no longer just a compelling hypothesis. It is evidence, a clue placed on the surface, waiting for a sharper eye to find it. Europa has, in a single discovery, shifted from a maybe to the solar system's most promising candidate for a habitable environment beyond Earth. This is the new chapter. This is the fruit of our cosmic contemplation. It is an era defined not by asking if we are alone, but by equipping ourselves with the means to search for an answer in the chemical compositions of atmospheres, in the dynamic maps of galaxies, in the corrected colors of planets, and in the molecular traces on distant ice. We have graduated from wondering at the universe's grandeur to interrogating its specifics. We are no longer just stargazers. We are now detectives. And the cosmos has just begun to yield its clues.